You often heard before that the novelty of the behavioral approach is to use psychological insights to bring more empirical realism into the models. Well, that in itself is not really very new. Psychologists have been doing that for centuries, and in marketing, people have been doing that long time. The real novelty is that these realistic insights are combined with the firm modeling of economics. We want to have firm quantitative predictions, and that we also do. So therefore, in this course try to teach you the behavioral approach in a deep manner. So I really try, like in the previous recording, you've been digesting quite some mathematical formalism, all kind of formulas. We had that as part of the behavioral approach, and then we must see how that can be connected with realistic empirical things. That's the thing coming now in this recording. The first example to show you how the rank-dependent formula can capture phenomena going on in the human minds empirically realistic. To illustrate, I'm going to assume a lottery probability distribution with 4 outcomes, each probability 1/4. They all have the same probability. And I'm going to depict here a weighting function, and this will be the square weighting function that we're going to use to see what happens. You see it's quite low, always below the diagonal, and as I'm going to explain, this function will enhance pessimism. Pessimism going on in the minds of people make that you always think that the bad things, if bad things can happen, they will happen. You pay more attention to that. The good things that can happen, you don't pay much attention to that. That will be happening here. That's what we're capturing, and I will explain. We'll do calculations to bring it out, to show it. We start with the decision weight of outcome 80, the best outcome. The rank of 80 is 0. There's no probability, no outcome rank better, so that probability is 0. It has rank 0. We add to that the outcome probability is 1/4. So there is 1/4. How much W gain do we get from that? And we do see it here, is that very small gain. It's in fact 1/16, W of 1/4. So quite small. Not much attention to the best outcome. Second best outcome is 60. The rank is now 1/4. And we add to that the outcome probability, so we end up at half. How much W gain do we get from that? And it's that difference. This is the decision weight of outcome 60. It's still small, though bigger than what we saw before. Now we go to outcome 40. Well, you start to understand how it goes. The rank of outcome 40 is half. Outcome probability 1/4 is added to it, so 3/4 it's in total. How much W gain do we get from that? It is this difference, already bigger than what we saw before. Finally, the worst outcome 20. The rank is 3/4. We add the outcome probability 1/4 to it, and how much W gain, there it is. That's the decision weight of outcome 20. So here we see how it works. And you see this function is given with the rank-dependent formula is given little attention for the best outcome 80, and the bad outcomes, they get a lot of attention. So indeed, that feels like pessimism. There is a little bit of a different, maybe a different reasoning to see why this is giving pessimism, and that is if you just look at the graph of the W function, you remember the W value of a probability P is the decision weight it had when it is the best outcome. So therefore the W function is sort of best rank weighting function, or how much it goes to the good outcomes. And if it's always low, then it means the best outcome must always be receiving low attention. And then you can already feel that will probably give pessimism. That will increase, because pessimism is indeed increasing risk aversion. That's what's probably happening here. But here these calculations show it maybe a bit more clearly. Indeed, that's what's happening here. And you can also see, differences of the W function. Often they tell you what the decision, not one function itself, but differences. So having maybe more to do with the derivative than with the function itself sometimes. In a particular region of outcomes, how much attention do they get depends on the derivative, the steepness of the function there. So with that in mind, let us look a bit more. Here we see all kind of small probabilities and small ranks. Small ranks, maybe they are the good ranks. They are about the good outcomes. So how the function is behaving is domain to the left. That tells you how the weighting of the good outcomes go. And you see it is shallow there, small differences, low derivative. So that means the good outcomes are not receiving much attention. Here the bad outcomes, these are big probabilities, so big ranks also. So big ranks are about bad outcomes. So this part of the graph tells you what happens to the bad outcome. And you see it's steep, big differences, much attention is paid to that. So once you understand how this function goes, and then you see the graph, then you immediately see, oh, you see where it is steep, so those outcomes have much weight. Then immediately, if you're a specialist in the rank dependence, you'll be getting it more and more. Immediately when you see the graph, you see me, oh, shallow here, little attention for the good outcomes. You immediately understand what risk attitude is captured by that mathematical function, and that is pessimism. This is indeed enhancing pessimism. Another graph, but you start to understand now how it works, is another graph, the square root function. Square root function is always overweight above the diagonal, overweighting all the outcomes. So then, if you know the W function is the weight of the probability, if it has the best rank, that's already a way to see you're having good big weights for the good outcomes, for the best outcomes. But then if you do this different reasoning, then here you see all the difference already. You immediately see it. Here, this is the region that speaks to the best outcomes. Function very steep there, big derivative, big difference, big decision weights, much attention for the best outcomes. This is the worst outcome, shallow, not much attention. So that's how the graph works. And now maybe you already get a little bit of a feeling how the rank-dependent formula can enhance risk attitudes and can give in phenomena about it. You can also see in this from these figures and these reasonings, the outcomes in that prospect, they all have the same outcome probability. So outcome probability doesn't do it, it's the same. And expect yield can't do anything, it only looks at the outcome probability. The difference of these outcomes is in the ranks, they have different ranks. So that, together with rank dependence, allow you to treat these outcomes differently, to weight them differently, and that way to bring in optimism and pessimism. So here you see a little bit this rank dependence, how it is operating, how it gives you new phenomena, new insights into risk attitude. So this was the first figure where you get a bit of that feeling, more of it to come. Maybe I can also say a bit from a historical perspective. I don't know if you know about history of economics, but some centuries ago, people had some difficulties working with utility. They didn't really, there were paradoxes. They didn't know how to handle situations. And around 1870 came what people called the marginal revolution. Some people started understanding that for many phenomena, what matters is differences of utility. And then margin is your derivative that gives you differences. In many situations, the differences of utility, rather than utilities themselves, are what you should look at. And when they look at that, they started working with marginal utility. Then suddenly all kind of phenomena became clear, all kind of things started working. That was a big breakthrough. The marginal revolution is called in history of economics. But Quiggin did something similar for probability weighting, the behavioral component of decision making. He showed in many situations we should not be looking at W in an absolute sense. This old formula of the psychology that didn't work. They were just using W in an absolute sense. And Quiggin had this mathematical insight that it is, and it comes out from his insight, that often you have to work with differences of W function. Then you see what is happening. That is impacting the real behavior. So in that sense, maybe Quiggin did in the behavioral approach what the marginal revolution did in 1870 for classical models. But anyway, it was a good insight, and we are benefiting from it, and that will be continued.